It's a pleasure for me to introduce Gada. I think that Gada, you have already before given some talks, right, in our seminar, I suppose. Yes, probably once, and also participated in some of our conferences. So it's a pleasure for me to introduce once again Gada Abi Yunes. Gada is a graduate student of the third year from Lebanon and also from France. And Gada will continue these presentations about aterosclerosis. And this time it's about hemataxis in aterosclerosis. It's a very interesting, exciting topic. So please, Gada, we are listening to you.
Thank you, Vitaly. Hi, everyone. As Vitaly told you, I am a PhD student at Klod Bernar University under the supervision of Nader Al-Khatib and Vitaly Volpert. First, I would like to thank the organizing committee for this opportunity to participate to this seminar. And as you can see from the title of this presentation, I will be talking about the mathematical modeling of the interaction of inflammation and chemotaxis in atherosclerosis and the role of this interaction in the formation of fatty streaks. So this work is a joint work with Maxim Kuznetsov. This presentation outlines the following points. I will start with a biological review on atherosclerosis, where I will be highlighting the interaction between chemotaxis and inflammation, and I will define what are the fatty streaks. Then we will move to the mathematical model. In this part, we are going to propose a complete model that describes the biological processes described in the first section. Then, for the sake of ease, we are going to reduce this model. I will show some results in the one-dimensional and two-dimensional cases. And finally, I will go back to the complete model to give some conclusions and results. So let us start. If you would like to define what is atherosclerosis, it is better to show this cross-section of the artery, where you can see that the arterial layers, that the arterial wall is formed of many layers. So by definition, atherosclerosis is an inflammatory disease that is characterized by the lipid infiltration in the first arterial wall called the intima. This is due to overlapping risk factors such as hypertension, smoking, diabetes, obesity, and many other risk factors. So the onset of atherosclerosis starts in childhood and then it progresses in time. So an initial lesion may become an advanced lesion that causes major complications such as stroke, aneurysm, heart attack. Let me draw your attention to the first two types of these lesions. So the first type, in fact, it is characterized by the intimal accumulation of lipids, and these deposits are can be detectable microscopically. However, in the second type, that includes fatty streaks, the lipid deposits are detectable or are visible to the unaided eye. So I will be talking about this in more details in few. So, as I told you, we are going to talk about the inflammation and the chemotaxis in atherosclerosis. Let us start with the inflammation. Again, here also we have a cross-section of the artery. You can see here the lumen, where the blood circulates. The endothelium, it is a thin layer that separates the blood from the arterial walls. And the intima, where the plaque forms. When the endothelium is exposed to cardiovascular risk factors, the endothelial cells become damaged. They allow lipid particles like low-density lipoprotein or LDL. They allow them to enter the intima, and they attract white blood cells such as monocytes to enter the intima. Once the monocytes are inside the intima, they become macrophages. So they release free radicals to oxidize the LDL particles. So we get oxidized LDL, and then they start to engulf or to ingest oxidized LDL in a process called phagocytosis. And at this stage, they release cytokines. So cytokines activate endothelial cells and promote the recruitment of new monocytes. The excess of lipid inside the macrophages gives it a foamy appearance. So at the end, we call them foam cells. Foam cells cannot destroy the oxidized LDL, so they release their content and form a plaque. So this is very briefly about the inflammation in atherosclerosis. Let us now talk about the chemotaxis of macrophages in atherosclerosis. So what does it mean, chemotaxis? In fact, it is the phenomenon by which macrophages move, and this movement is directed in response to a chemical gradient. So very briefly, I am not going to talk about a lot of details, but let me tell you that epidermal growth factors that are produced by endothelial cells mediate the chemotactic activity of macrophages. Now we can say that somehow there is a positive feedback between inflammation and chemotaxis. Let me explain how it works. Macrophages ingest oxidized LDL, so they release cytokines, and these cytokines activate endothelial cells. Activated endothelial cells in turn produce EGF or epidermal growth factor, and these EGF mediate the chemotaxis of macrophages. Then macrophages can move towards oxidized LDL to phagocyte it, and so on. So there is a positive loop between inflammation and chemotaxis.
Gada, could I ask a question? Do you understand that this scheme, this was a principal scheme, and in fact, macrophages are go from the lumen, so EGF should be EGF is works in the blood flow to recruit macrophages. Yes.
No, EGF works here within the intima.
Is it? But macrophages are recruited from blood flow. Yes.
Yes, they are monocytes in the blood flow and macrophages in the intima.
And this EGF, which are produced by inflamed endothelium, or does it? What cells does it recruit? Cells from blood flow or cells from, I don't know, elsewhere, from tissues? Does blood flow act on EGF?
Let me maybe help to clarify certain things. Of course, what Gada presents here is a simplified version of all this very complex process. In fact, to answer the question asked by Alexei, we should recall that there are two different things among the others: pro-inflammatory cytokines and EGF. Okay. Pro-inflammatory cytokines are produced by macrophages and foam cells. They are shown as I don't see here on this figure whether they are shown or not. But anyway, these pro-inflammatory cytokines, they go to the endothelial cells and they activate these endothelial cells. When these endothelial cells are activated, their receptors, they activate their receptors towards the blood flow. From the side of the blood flow, the receptors are activated. Monocytes, which are shown here in the lumen, in fact, they roll from the side of the flow in the lumen, but on the surface of the endothelial cells, they roll just like a balloon. Yeah, on the ground, they roll like that. They come to the place of inflammation where these receptors are activated. And these activated receptors stop these monocytes rolling. These monocytes stop and they penetrate inside the blood vessel wall, the intima, as it's shown in the figure, as Gada shows with the cursor. Okay, so monocytes penetrate the vessel wall from the blood flow. After that, they become macrophages, they phagocyte, all these lipids, oxaldehyde, things like that. But, and here this other stage comes into play, this hemataxis. On the other hand, this activated endothelial cells produce this endothelial growth factor. And it is this endothelial growth factor, it is distributed in the vessel wall. And macrophages, they can feel this gradient. You should understand that hemataxis is a very general physiological phenomenon. Many cells can feel the gradient and move of some molecules and move to the place where the concentration of these molecules is larger. So this is here we have this positive feedback which Gada mentioned just before. Endothelial cells answer to inflammation, produce all this, well, in particular endothelial growth factor, and as a consequence of this, macrophages move to this inflammation place, produce even more inflammatory cytokines, and recruit even more monocytes because of that from the blood flow, and activate even more endothelial cells. So this is how it works. Okay.
So here you consider the movement of macrophages that are already inside blood vessel wall to the endothelial cell from below.
Right. But then in the model, Gada will explain it in more detail, and in the equations we will see all these different terms, and I think it will become more clear.
Okay, thank you.
And may I have my small question? In the normal condition, there should be no monocytes in the endothelial wall, yes?
In the
normal condition, when
the arterial wall. In the intima, you mean?
Yes, in the intima.
In normal condition, yes, there are resident macrophages within the intima.
But they don't produce these inflammatory cytokines.
But we do not take into consideration here.
Thank you.
You're welcome. Do I proceed?
Yes, please continue.
Okay. As I told you from the title, we would like to study the role of the interaction between inflammation and chemotaxis on the formation of fatty streaks. So what are fatty streaks? I recall that the fatty streaks are the first grossly visible lesions, and they are multiple layers of macrophages or foam cells with lipid droplets. So if you look at these figures, these are cross-sections of an artery. You can see the yellow patches or spots over the arterial wall. These are the fatty streaks. We can notice that their distribution is not homogeneous. However, in this figure, their distribution is nearly periodic, if you look at this section here. So,
and what is the difference between streaks and plaques? Or they are the same?
No, they are not the same. I will go back to the first slide to show you what is the difference. When here we have the development, the progression of atherosclerosis. When we say fatty streaks, we are in the early lesions. Sometimes fatty streaks are reversible, so we do not call them plaques. So starting from atheroma, when we start having this dark yellow, if we can call it like that, from this stage we start to have a plaque. And this plaque becomes dangerous in the future.
Mm-hmm. Okay, thank you.
You're welcome. So maybe some of you have worked on atherosclerosis and know already that the blood flow may influence the formation of plaques. So maybe some of you will ask, what about the influence of blood flow on the formation of fatty streaks? Should we take it into consideration in our study? So let us look in a close way to this figure. These are arteries, and this is a research that detects the formation of fatty streaks and plaques. The vertical lines refers to the formation of fatty streaks, whereas the horizontal lines refer to the formation of plaques. We mean by this a more advanced lesion. So we can notice that fatty streaks in general form along the whole artery, while plaques form more often near vessel bifurcation. So we can say that the early development of atherosclerosis is not determined by the flow. So in other words, the flow does not influence the emergence of fatty streaks.
And could you please explain, well, first of all, these are two different examples. Or first my question is for example left feature, is it one example, or it is a combination of maybe many investigations?
You mean this one?
Yes.
Okay, in fact, it is a research done over the arteries of 6 animals. And because we do not have a lot of, let's say, information about the formation or the location of fatty streaks, so we rely on this, on this research. But I don't know if it is a combination of many research or not, but it is published and...
Oh, sorry. I think that in the left figure, there are 2 columns, and each column corresponds to one mouse. So in fact, the 6 animals, it's six mice, 2 of them in the left figure and 4 of them in the right figure. And the left figure is, I think it's written here, it's after 5 months of fat diet. So they took these poor mice and they gave them a lot of food. and then they looked what happened with them. So in the left figure, these are these mice after 5 months of fat diet, and in the right figure, another 4 because unfortunately these mice were sacrificed, of course, after that. So other 4 animals in the right figure after 8 months. So, and these 2 figures show this progressive development starting from fatty streaks and then to atherosclerotic plaques. So this, in this particular paper, what we found were with this very detailed data. Yes, there are only these several animals. In principle, of course, it's a very important, you can imagine, very important subject, and there are many works devoted to formation of fatty streaks or to plaques, with a lot of data where and how they form. But it is really difficult to find such detailed data, especially on the formation of fatty streaks, because it's very early stage of the development, and not so many data available. It's more difficult to observe this. This is why we mostly in this work we are mostly based on this work, but less detailed data they can be also found in other works.
Okay, so the general conclusion here is that plaque development is not guided by flow, or not determined by flow. So why is it concluded so?
Well, this is a very important point.
I don't understand.
You don't understand
really.
What the role of flow, or what is your
the
question?
conclusion? I don't
the conclusion is yes.
Yes.
The conclusion, yes. The conclusion is that fatty streaks, as Gada just told us, fatty streaks can be formed everywhere in the vessel. They are not related to bifurcation points. Why bifurcation point? Because very often, and this is true, formation of atherosclerotic plaques, meaning more developed lesions, are related to vessel bifurcations. Why to vessel bifurcations? Because flow is perturbed around, basically after the vessel bifurcation. So the flow is perturbed. There are vortices. There are backflows. There, in some places, reduced shear rate, and all the things, perturbations, turbulence, low shear rate, they act on the endothelial cells. And these endothelial cells, they can become damaged or activated, and all that promotes the development of atherosclerosis. This is why very often formation of atherosclerotic plaques, meaning advanced lesions, are related to vessel bifurcations. And this is the point of this work, that formation of fatty streaks early, just the beginning of this formation of these lesions, they may not be related to blood flow, and they are explained by other factors.
In this case, one can conclude that plaque development is not determined by the perturbed flow, because well, everywhere here flow does exist. We do not have here no flow conditions, so flow is everywhere, and so we cannot conclude that atherosclerosis is not determined by the flow. But,
I agree. By flow perturbation, of course, flow is present.
Yes. Okay.
But this early regions, well, of course, all this kind of a little bit hypothetical. But well, our main working hypothesis is that indeed flow is present, but it does not influence the formation of these early lesions called fatty streaks.
Okay, thank you here. Thank you.
Okay. So here we can conclude once again that the flow does not influence the emergence of fatty streaks. So we talked about the interaction of chemotaxis and inflammation on one hand, and on the other hand, we introduced the emergence of fatty streaks. So we make the following hypothesis. Does this interaction between chemotaxis and inflammation influence the emergence of fatty streaks? We are going to answer this question by the following mathematical model. So we propose this mathematical model that describes the processes that we talked about earlier. So this is a system of 4 partial differential equations of reaction diffusion type. Here we model the evolution in time of the concentration of monocytes M, cytokines A, activated endothelial cells E, and EGF 4G. The first right-hand side terms in equations 1, 2, and 4 are the diffusion terms, and the last right-hand side terms in these equations are the degradation terms. If we look at this term, in fact, this term determines the chemotaxis of macrophages, and here the flux of M goes in the direction del G over del X because EGF mediate the chemotaxis of macrophages. While this term here, it models the recruitment of monocytes due to the presence of cytokines denoted by A. This coefficient alpha 1, in fact, it refers to the beginning of the inflammation. So it describes the lipid accumulation within the intima that triggers the inflammation. This term here describes the production of cytokines due to the presence of macrophages and the cytokines themselves, because cytokines are in fact involved in their own production. Now for the equation of activated endothelial cells. This is the term of the activation of endothelial cells. This activation is due to the cytokines, and it is proportional to the difference between the total concentration of endothelial cells and activated endothelial cells. And this term models the deactivation of endothelial cells. And finally, the second right-hand side term, this is for the production of EGF by endothelial cells. Now here,
Gada, could I please ask another question? Well,
yes.
You solve your you write your equation on the some section along x coordinate, and as I understand, E is on the one side of this edge on the vessel wall, and another, all other variables M, A, and G are distributed. Yes. So, yes. For example, well, I am interested in the first equation in the term which describes the production of M. So you consider that this term describes the activation of monocytes, yes? Or production. What is it?
The production.
Yes.
The production.
No, it's not. Well, sorry, it's not. It's not really production. I would say that it's recruitment of monocytes from the blood flow.
But if it is recruitment from the blood flow, then this term should be in the boundary conditions for this equation.
Gada, will you answer this question?
You want to talk about the free boundary problem?
No. Well, okay. Let me talk. Well, in fact, yes, of course, you are right. If we consider, for example, two-dimensional problem, where like you can think about a rectangular domain where the interior part of this rectangular corresponds to the intima, meaning to the vessel wall, then the upper side then of this rectangle is this endothelial layer, and then indeed there is influx of cells through this upper wall inside the rectangle. It's absolutely true, and indeed we have considered also such kind of two-dimensional problems exactly with these nonlinear boundary conditions which determine the influx of monocytes depending on the concentration of pro-inflammatory cytokines denoted A here. It is also possible to consider a simplified one-dimensional formulation, and in this case, this term doesn't enter the boundary condition, but it enters the equation similar to the reaction terms, but its biological meaning, it's not reaction, but influx from blood flow.
So this term assumes that monocytes or macrophages are equally distributed very quickly across the vessel wall.
You mean in the direction perpendicular to the?
Yeah. Yes.
Well, right. We can say like that. Yes, indeed. In this simplified model, one-dimensional model, we don't take into account this distribution in the perpendicular direction. If the wall is sufficiently narrow, this is justified. But indeed, in a more complete formulation, we should consider this two-dimensional or three-dimensional model with nonlinear boundary conditions. Right.
In this case, I don't understand completely nothing, because your second term is the term of hemataxis just across the vessel wall.
No, sorry, not across the vessel wall, but along the vessel wall in the longitudinal direction.
Right. So X is the.
It's right. It's in the axial. Right, in the axial direction. Right.
Okay. In this case, the feature should be placed here, because I thought that X is okay. Thank you.
Yeah, maybe, Gada, by the way, maybe it's better than the next time to show this figure with the axis, and maybe it will be more clear. Okay.
Okay, thank you.
So we move to the reduced model. And this model, while we provide a reduced model, it is a more generic model where we keep only the equations for M monocytes and A cytokines. So here, in this term, the flux of macrophages goes in the direction del A over del X, because in this model, we do not take into consideration EGF or endothelial cells. So what triggers the chemotaxis of macrophages are the cytokines due to the positive loop that I explained earlier. The stability of the ODE of the reduced model gives the following. So here we have the following fixed points that exist. Here we show their existence and stability according to the values of the parameters. So clearly, we can see that we may reach the monostable cases or the bistable case. Each point has its biological description according to its own components. So, for instance, S0 corresponds to the disease-free state, and SR corresponds to the inflammatory state. So, this point SR is always stable if it exists. And SL, this point corresponds to a threshold between the disease-free state and the inflammatory state. Now, if we move to the stability analysis of the spatial model, we linearize the system, the reduced system, about the stationary point SR, the inflammatory state we need. Then we have the following eigenvalue problem. We look for solutions of the form m equals p cosine kx and a equals q cosine kx, and therefore we have the following eigenvalue problem. Now we notice here that in this term we have the coefficient r. This coefficient multiplies the hemotacsis term in our model. So let me recall that the point SR is stable for r equals 0. As I told you, in the ODE system, SR is always stable, and in the ODE system, R is taken to be 0. But what about when R is strictly positive? In fact, the analytical study, the calculation lead to that for certain values of R, the stability of SR does not always hold. So we have this minimal value or critical value for R, for which the loss of stability of SR occurs. So, in other words, when R is greater or equal to R0, SR is no more stable because the eigenvalues are no more strictly negative. Now I will show you some numerical results, and I will talk about the loss of stability. Let me first explain what we have in these two figures. In the upper figure, we have the solutions for the variable m and the one-dimensional model for different values of r. So here we can see that we have constant solutions and we have solutions showing periodic spatial structures. If we move to the second figure, it is about the amplitude of the solution depending on the values of R. So here, in this case, for the parameters chosen, R0, the critical value of R, is about 0.29. It is the blue cross here. If R is less than R0, then the amplitude is 0 and the solution is constant. Otherwise, when R reaches R0 and gets bigger, we can see that we have that the spatial structures arise. That means that the loss of stability occurs for R greater than R0, and this leads to the instability of the uniform distribution of the solution SR. So here you can see...
Gada, could you please remind what are the boundary conditions for M and other space variables?
In the reduced model, we took Neumann boundary conditions for the boundary.
Neumann, so the flux is 0. Yes, okay, I see.
Okay. So in the first figure, we can see branches of solutions with different amplitudes. So this branch corresponds to this branch here. This one corresponds to this one here. And this one corresponds to this one here. These results were obtained by using the continuation method. I will explain this very briefly. In this continuation method, we took decreasing values of R. So we start by R equals 0.5, and we find the solution. This solution will be the initial condition for the next simulation with R smaller than 0.5, and so on. So we notice that here the amplitude decreases and there is a jump. The solution reaches another branch, and for a given value of R here also there is another jump, and at the end, when R is less than R0, the amplitude is 0. So we notice that here we have 3 different branches. Suppose that we are on this branch. What happens if we increase, for example, the value of R? And same question here. What happens if we are on this branch and then we increase the value of R using this continuation method? The result is the following. Let's say we are decreasing R, we reach this point, and then we jump to the next branch, and then we increase R, then we are going to reach this branch here, this part here. By decreasing R once again, we reach this first branch, then we increase R to complete this branch, and then decrease it in order to reach these points. So here is, this is what we call the bifurcation diagram. First, we notice that for a single value of R, for example, if we take the 0.45, we may have 3 different solutions depending on the initial condition. And here we have a bifurcation point. We can see that the solution at the first branch is stable directly from the bifurcation point, and the trivial solution becomes unstable. This is what we explained earlier. Other branches also bifurcate from the trivial solution, and since the solution is unstable for the corresponding values of R, solutions at the second and third branch are unstable near the bifurcation point, whereas for larger values of R, they are stable. Before we proceed, I will give some conclusions and biological interpretation in order to understand what we are going to get later. So for us, the stationary solution SR describes the formation of lesion of type 1, the type that I told you it is detectable only microscopically or chemically. Whereas the spatial structure refer to the emergence of fatty streaks, and they determine their heterogeneous distribution. Why we say that the spatial structures refer to the emergence of fatty streaks? Because the structures feature the formation of the multi-layers of foam cells that I explained at the beginning of the presentation. Of course, the chemotaxis causes the spatial structure to arise, and we can say that chemotaxis influences the shape of fatty streaks. And a final conclusion here is that when we increase the chemotactic activity, there is a rise in the fatty streaks peaks, because when R is bigger, the amplitude is bigger. Now we are interested in studying the influence of the inflammatory activity on the instability of the uniform distribution. So here we can see that we are studying the dependence of R0, the critical value of R for which the loss of stability occurs, depending on alpha 1, that is the rate of intimal cholesterol accumulation, and alpha 2, the rate of cytokines production. We can see clearly that when alpha 1 or alpha 2 increase, then R0 decreases. So when there is more accumulation of cholesterol or more cytokine production, even a small chemotactic activity may lead to the emergence of fatty streaks. Or, in other words, the oxidized LDL and cytokines favor the emergence of fatty streaks. And this result holds biologically, it is valid. Now, we would like to see what happens to the integral of the solution, how the integral of the solution that we get depends on alpha 1, alpha 2, and R. So, we look for the area below the solution, and we notice that when alpha 1 or alpha 2 increase, this area increase. However, when R increases, the area decreases. So what does it mean? The integral of the solution A, or the area below the solution, refers to the size of the lesion. The elevated levels of cholesterol and an elevation of cytokines production contribute to an increase in lesion size, because when alpha 1 and alpha 2 increase, A increases. So this is biologically also valid. It is in line with the biological knowledge. Moreover, we noticed that when we increase the chemotactic activity, when R increases, the area decreases. So this system suggests that an elevated chemotactic activity stimulates a compact accumulation of macrophages. So, due to the chemotaxis, macrophages accumulate or form layers in a compact way, and this diminishes the total area or size of the lesion. Here I show you the wave propagation or the solution in 3D. First, this is a solution for M, and this is a solution for A. The initial condition is a step function, and here, if you can see it in the solution M, there are in fact two propagations. The first propagation is the propagation towards the point SR. And the second propagation is the propagation of the spatial structures.
Sorry, I don't understand this.
Yes. Okay.
What is the just a second?
Okay. Suppose that there is no chemotaxis. If we take this initial condition and simulate the code, we find a solution that goes towards the constant stationary solution SR. Okay, so here is the value of SR. Here we can see that the solution propagates towards SR. However, since we have chemotaxis and R is large enough, it is greater than R0, then we will see the spatial structures, and these spatial structures also propagate with time. So here there are two different propagations. I don't know if it is clear in these figures that let me show you the projection of these solutions onto the X and time space plane, sorry. Maybe this time it will be more clear. So here is for time t0. Here we have a small perturbation, and then we can see this first propagation towards SR, and here's the stripped area. This is the propagation of the spatial structures, because these lines are the peaks of the spatial structures.
I'm afraid I didn't catch what is SR. So here you have two steps. Yes, the first step from 0 to SR, varies from dark blue to blue, and then to red one. So what is SR? I don't understand.
Yes. SR
What's it about?
SR is the constant stationary solution, and if we go back, let us go back to the ODE model. Okay, so this is SR here. It is fixed.
Ah, okay, I see.
Okay, it denotes the inflammatory state.
Yeah, okay. So from 0 to SR. Okay, I see.
Okay. So here, these lines, in fact, as I told you, this line refers to the propagation towards SR, and the line, the oblique line formed by the border of these lines here, refers to the propagation of the spatial structures. So, in other terms, the slope of this line is the velocity of the propagation of the solution towards SR, and the slope of this line is the inverse of the velocity of the propagation of the spatial structures. Now, we have two different figures, A and B. In B, it is the same, but here we have a greater R, so a higher chemotactic activity. We can see that this line remains the same if we compare M to M and A to A. So that means the velocity of the propagation of the solution towards SR remains the same. However, the velocity of the propagation of the spatial structures becomes bigger. So the more chemotaxis of macrophages is, the faster will be the emergence of fatty streaks over the arterial wall. Here I show you the result of the simulations in the two-dimensional case.
Gada, could I please ask another question?
Yes.
Well, the main point here is that you have here a hemataxis flux in your first equation, so it could be expected then some sort of non-homogeneous distribution of M due to this flux can be expected just somewhere near the boundary, near the moving boundary between SR and upper concentration. And in the previous figure, it seems that the distribution, yes, well, it can be hardly seen, but it seems that all is nearly homogeneous between fronts. You have here two fronts, and it could be expected that some migration of cells, say from right to left across the front, could be expected, but it is not the case. Okay.
Well,
Vitaly, do you understand what I mean?
Yeah. Okay, let's discuss. Gada, I think it's also a useful experience for you to answer these questions. So yes. So in the left figure, as Gada explained, we have two different things. The first one is this propagation from zero state to this inflammatory state, which is shown here is this light blue color, right? And then since spatial structures emerge slowly. It takes some more time before the structures emerge from this inflammatory state. This is why there is some distance between the first front and the second front. Of course, if we look at it very closely, at this distance between them, we will see decaying oscillation. So this, in the center, we have this periodical structure, spatial structure. If we move from the center towards the border, so these oscillations, the amplitude of these oscillations will exponentially decrease. So from here, so just if we move a little bit further, so we just don't see them by eye, but if we look at them more precisely, yes, we can see small decaying oscillations from the center towards the border.
Really,
so,
there are even
yeah.
oscillations, not simply, well, some holes or but even oscillations.
Spatial structure, the periodic spatial structure. No, not time oscillations, space oscillations.
Yes, space. Yes.
Oscillations in space. Yes, it is a constant. It is a stationary in time, stationary solution. Stationary solution. This periodic structures, they're stationary. They don't depend on time when they just fully developed. But during their development, they already emerge. But the amplitude decrease exponentially from the center towards the border. So, well, exponential decrease is rather fast. So already in this light blue area, we just don't already see the spatial structure, and they look like it looks like a homogeneous in space solution, but in fact it is not. There are some small oscillations.
Can we see these oscillations, these space oscillations, in the previous slides?
Yeah, Gada, please show. Yes. This is the case. Yes, I think it more corresponds to the figure B in the next slide, where this speed of propagation of this structure is large enough. So in fact, they merge, this two front merge. I think it's rather corresponds to this case. Maybe not exactly. I don't know.
It corresponds to the first one, but in the
to the first one. Okay.
Time till 100.
Okay, so there is this light blue area, like this SR state, can be seen here.
So we see here, if we look for time t equals 200, then we see that after the front we see great oscillations. Yeah. So the oscillations from 15 to say 5, I don't know. And we see that there are 1, 2, 3, 4, at least 4 oscillations I see here from x equals 0 to 40.
Something like that. Yes, something like that. Yes.
Okay. So this means that, but yes, this means that this plaque should migrate. These oscillations means that plaque should migrate along the wall.
No. The plaque does well. First of all, let us call it fatty streak, not plaque, because plaque it's as we discussed previously, it's different. But it is stationary. It emerges. It does not move anymore. But the area covered by this fatty streak, it grows in time.
Mm-hmm. So they stay. Yes, I see. They stay. Yes. Okay. Thank you.
Okay. Now here are the results for the two-dimensional model, the results of the simulations. The simulations in A, B, and C are for different values of R, in fact, for increasing values of R, and you can see that the domain here is a square. So the initial conditions are slight non-homogeneous perturbation of the uniform state SR, and this perturbation lead to the emergence of these patterns. Now, if we go back to the complete model, we can do the similar study. So we can find the stationary solutions. We can do the linearization about the point SR. We can also determine the eigenvalue problem and find a critical value for R0, so similar to the reduced model. And here I show you some simulations for this complete model for different values of D3. I recall that D3 is the diffusion coefficient for the EGF. Now we can see that, for instance, for different D3s, the solutions are very close. And as a final conclusion, similarly to the reduced model, the emergence of spatial structure in the solution of the complete model is also due to the chemotaxis term. And since these spatial structures refer to the emergence of fatty streaks, we can conclude that fatty streaks appear due to the interaction of chemotaxis and inflammation in this complete model. And thank you for your attention.
Thank you very much, Gada, for this very interesting presentation. It was very nice, and we had also many questions, also nice discussion. So please, if there are other questions, comments, so please go ahead. Well, while our audience thinking about possible questions, if there are some, so please return to these two-dimensional figure simulations. I think that this is quite interesting, but in this particular work, it's just some numerical examples. It's not a systematic study of this two-dimensional problem. It becomes a little bit more difficult to study it. Numerical simulations are a little bit longer. And moreover, the convergence rate to these stationary solutions is quite slow. This is why it takes more time. And this is why in this work we just stopped on the several examples. But what we see here, just some interesting points. First of all, the general point is that you see it's really fatty streaks. Streaks means stripes, poloski, right? In Russian, poloska. So these are really streaks. So really this like lines of this this is why in fact they are called fatty streaks, because they have this geometry, and this is what we observe in simulations. Maybe this is a coincidence, I don't know, but maybe it's not really coincidence. Maybe it really works like that they have this geometry like that. But we could not yet study this the emergence of this geometry and how this geometry depends on parameters, because we see here there are three different examples for three different values of R, the schematactic coefficient. So the geometry is different a little bit. Well, it's natural to assume that there are complex, like nonlinear behavior, all these bifurcation diagrams, multiple solutions, because we see in the one-dimensional case, Gada presented this multiplicity of solutions. This means that for the same value of parameter, we can have different stationary regimes. And certainly all that also plays here and makes this modeling more difficult, because depending on the initial condition, we can obtain different solutions with different structures. What is also interesting here is that in some rare cases, Gada showed in the beginning these experimental pictures with two different like geometries. One of them was really fatty streaks really the stripe structure. Of course, not so geometrically precise as in simulations, but some in the left figure, something like this stripe, something like oriented, maybe in the direction of flow. Alexei asked the question about the role of flow. We don't know what is the role of flow here. Maybe the orientation of this plaque, of these fatty streaks, somehow related to this flow, but they have this kind of direction, right, in the left figure. But in the right figure, this is completely different. And in fact, we searched a lot of literature, and the only evidence, the only photograph we found with the structure like that, with this, I'm not sure that I don't think it is called fatty streaks. Maybe it is called fatty dots. I think that I saw somewhere this fatty dots, and it's really better corresponds to the structure. But it's really very rare. This is the only place where we found such a figure, and we did not see this case in numerical simulations. And this would be really interesting to continue with these two-dimensional simulations to see whether we can obtain different geometrical structure, in particular these dots more or less periodic. This is what I, yeah, please.
Yeah, I want to say that, well, there could be many possibilities and many factors which can lead to this or that geometrical pattern on this plane or on this wall. And in fact, in mathematical biology, you know that there are lots of works, for example, how strips on the zebras emerge and all the stuff. And well, first of all,
sorry, but the mechanism is different. All these patterns, in particular for the animal skin and in many other situations, they model with Turing structures. The mechanism is different, and the variety of different geometries in Turing structures is just huge. And indeed, it can be this spot patterns or stripe patterns, things like that. I don't know exactly about hemataxis, what kind of patterns can be obtained in hemataxis. I just cannot say that right now.
Well, we may suggest that many people studied some influence of hemataxis on spatial structures. I don't know, but well, what I wanted to say is, first of all, well, maybe it could be useful to study not the structure, but the size of these strips and to relate them to experiment, because this is the only parameter, this is the only value, but well, the structure is more harder to relate to numerical simulations. Okay, but the value you can extract some dependencies from model and from experiment and compare these characteristic sizes of the structures.
Yes, right. Gada, I don't remember. Could you recall, please? I think that in the previous work you have done some parameter estimates, no? Not for hemataxis, but for the wave speed, for the plaque growth rate. Did you do it? Yeah, I think. Yeah. So Gada, in the previous work, Gada has done some parameter estimates, but indeed it was not done for the hemataxis and for the size, for the characteristic size of this fatty streaks. And I think it's a good suggestion. So Gada, you can think about it.
Okay.
And well, I have another suggestion. When I asked about HGF and how HGF acts in recruited macrophages. So yes, here, and you told me that here it works only below the endothelial cells. Well, I don't know, maybe it first of all works in the flow and somehow influenced by the flow. And next, when you have white blood cells rolling along the wall, okay, and then you have the plaque growth, or maybe type growth, but it acts, it perturbs the rolling of these white blood cells along the wall. So maybe there could be some positive or negative feedback loop. When plaque starts to grow, then recruitment of macrophages from blood flow can be increased on the leading edge and can be decreased on the back edge of this plaque. Because I know that for platelets, this works really exist. People study how platelets are recruited from blood flow to different from different directions to the growing thrombus.
Yes, right. So I'd like just to recall that in fact there are two, well, as we discussed previously, two different molecules. These activatory cytokines, we call them A, which determine the influx of monocytes in the vessel wall, and then another molecule is EGF, which determines hemataxis of macrophages. So in these fatty streaks, as it was shown in the experimental results, in fact, the whole wall after this fatty diet becomes inflamed, and monocytes penetrate everywhere in the wall. This is because of this inflammation. But then because of EGF, they begin to accumulate in the spatial structures. So yes, there are feedbacks in all this process, but there are several two different molecules which determine influx of macrophages or monocytes and the hemataxis.
So the main point here that hemataxis serves to accumulate.
Yes, to aggregate. Yes, to aggregate. Yeah. Well, in fact, this is our hypothesis. I mean, the point of this work, yes, that the interaction of this inflammation and hemataxis leads to the emergence of this fatty streaks. Fatty streaks, by definition, this is already non-homogeneous distribution of lipids in the wall. And by the way, this is, as Gada also mentioned, this is yet a reversible stage. So after this several months of diet, of fat diet, if after that we put these mice on low-fat diet, these fatty streaks will disappear. But if they continue several more months, then the plaque will form, and the plaque, it's already irreversible stage of atherosclerosis development.
Yeah. Thank you. Thank you.
Okay, thank you for this interesting discussion. Other questions or comments? If not, then Gada, thank you again for this interesting presentation and for this participating in this discussion, of course. And please also some suggestions and questions, please try also to take them into account. Okay, thanks also for our listeners, and our seminar is finished for today. The next one, I think, in 2 weeks. And at this point, bye for now. Have a good day.
Okay, bye-bye.
Bye.
Thank you.
Thank you. Bye. Thank you very much. Goodbye.
Bye.